In the last several lectures, we have talked about elements of quantum computing, and we have culminated our discussion with the discussion of two major algorithms, namely a search algorithm due to Grover and the factorization algorithm due to Shor. Towards the end of the last sessions, we also talked about how quantum codes are corrected. So now we are ready to talk about the quantum communication various protocols. But before we do that, let us try to understand what does information actually convey. In this lecture and the next, I will be talking about elements of classical information theory. So if you look up the definition of the word information in a dictionary, you will find it says it is facts provided or learned about something or someone. This is quoted from Concise Oxford Dictionary. In colloquial parlance, by the word information, we understand a piece of knowledge. But the question is, does every piece of information convey something? Now, what determines if one piece of information has a richer content that is more important than another piece of information? And more importantly, since we are talking about science, how does one quantify information? Because in common day usage, the word information is not generally not quantified. It is understood purely qualitatively. So let us look at, to make up our ideas clear, let us consider a statement which says it is cold in Mumbai today. Now, does that statement inform us something? Is that good enough information? Now the point is that look at that statement. It says it's cold in Mumbai. Now what do we mean by cold in Mumbai? Is it colder compared to Alaska? Or is that a time information saying that it's colder than what it was yesterday? In other words, though this statement, it is cold in Mumbai, could inform you something in connection with a Bombay resident who sort of roughly knows what you are trying to say. But if you want to convey this to a wider audience, you have to be more precise than what you have done. So first thing that we do is this, that let us define what is cold. Suppose, looking at Indian climates generally, we define that I will say that a day to be cold if the temperature range is between 17 degrees to 22 degrees centigrade. Now, so in that case, if you make a statement it is cold in Mumbai, you have now got some information that the temperature is between these two ranges. But the information, though it is better, it doesn't tell you whether it is 17, 18, 19, 20, 21 or 22. So in principle, there is an equal probability, each 1/6, of the temperature being any one of these values. Now, so we would then say, all right, to find out the temperature, and there are 6 alternatives which I have given here, why don't you just throw a die and decide what is the temperature? Now, this is one way of doing it. Of course, it will not measure the temperature, but you will get some idea. Now, suppose I made an additional information. I said yesterday's temperature was 19 degrees and it is colder today. Now you notice we have done something better. We have now said that our information has become sharper and our temperature range have now become smaller. And supposing I had just 2 alternatives left, then I could actually toss a coin and decide what the temperature was to certain degree of accuracy. So therefore, information in some sense is a measure of uncertainty associated with it. You notice the difference. What do I mean by a measure of uncertainty? See, when you get a definite piece of knowledge, it doesn't remain uncertain anymore. So supposing somebody now tells you that yesterday the temperature was actually 21 degrees and you had thrown a die and had got certain number. Because throwing a die and getting a number between 17 to 22, as we have talked about, only give you that particular temperature could be correct with a probability of 1/6. But when you get the information what the temperature was today, your uncertainty is removed. So in other words, I need to somehow or other quantify this uncertainty, and then I have a measure of the information. Just to give you another example, that supposing you find there is a light which is steadily burning on the top of a hill. Does it give you any information? The answer is no. But on the other hand, if you see that light is getting switched on and off with a particular frequency, then you know maybe somebody is trying to communicate something to another person with a code. So in other words, the uniformity of light was not something which gave you an information, but the fact that there has been a variation of the information gave you some idea about what that it could have been a code. Now, talking about this, the amount of uncertainty which we need to define quantitatively, there have been generally two approaches, and we would be actually taking one of them. The approach which is due to Shannon, it essentially tells you what is the number of bits that needs to be transmitted in order to select the correct answer from a list of previously agreed choices. Now, in other words, what I do is I ask a set of questions, and this will give rise to, as I will show you in an example, what is known as a decision tree. Now, there is an alternative approach to this which is due to Kolmogorov and Chaitin. Now, what they look at is the complexity of a message. Now, just to give you an idea, supposing I have a message, let's say 200-bit message. Now, you say 200 bit is fairly long, but suppose I have that string as 10101010, etc. up to 200. Now, the length of the code that you need to write down in order to communicate this string is a fairly small code. That is because you will be simply using the fact that you use a do loop, as we say in computer language, and say it is 10 repeated 100 times. It's an extremely short code. But on the other hand, supposing that bit of 200 string was an absolute random variation of ones and zeros, then you need a much longer code. In other words, the complexity of the algorithm becomes more if the message gets more complicated. So that is the algorithmic approach due to Kolmogorov and Chaitin, which you do more in computer science, but I just thought I should simply mention it. Now, Shannon's thing, as I told you, is that you have a set of choices. So I ask a set of questions, and your answer should be in yes or no. And the way I quantify the information then is how many questions need to be asked in order to arrive at an answer. Now, I'll give you a sort of rough example. Supposing we want to decide on inviting a celebrity for an event, and our options are these people whose names are very well known. And notice that what I have done there is to give you a set of 8 names. And not only that, these 8 names have certain structure, and the structures that are there are 4 of them are Indians and 4 of them are non-Indians. Then I have people belonging to various professions there. There are people there who are sports people, film people, people in public services, and also 2 authors. Now, what I want to know is that supposing I want to select one person out of this 8 by going on asking questions to select a particular person, what I get is what is shown here in this slide. The question that we ask first is the person an Indian? Now, there are 2 options. The answer could be yes or it could be no. Alright. Supposing the answer is yes, Now you see, there are 4 Indians in that. So therefore, the first group with an answer yes, it has 4 possibilities. In the second group with the answer no, there are also 4 possibilities. Now I associate with every yes a bit 0. Alright, so I have come to the first bit, the leftmost bit to be 0. Now I ask the question, is that a male or a female? If the answer is yes, again I pick up a second 0. If the answer is no, I pick up a 1. Now each one of these groups have 2 answers. So then I ask the question, is that a public figure? Now if the answer is yes, then your choice is already known, that we are probably talking about Prime Minister Modi. And if the answer is no, because it was a male and the remaining 2 people are female, so the answer has to be the author, which happens to be Vikram Seth. Now supposing the answer was no, and we then ask, is that a sports personality? Now you said yes, I pick up a third 0. Then we say if it is sports personality and a female, so it has to be Sania Mirza, and if it is no, then it has to be the actress. So you notice now what I did. I said, I asked a few questions. Now I can count the number of questions, and you look at the number of questions that is there in this case. So you notice here, I have question number 1 first with an answer, then I ask a second question which I get an answer, then I get a third question which I get an answer. So I need to ask 3 questions to get answers in this case. And I can associate a bit, unique bit, which is, for example, in the first case Modi it is 000, for Vikram Seth it is 001, etc., etc. Now let us go to a mathematical quantification there. So decision tree is one way of quantifying information. That is, how many bits of communication that you need to convey in order to arrive at a particular answer out of a previously agreed set of alternatives. That's one way, it's called a decision tree. The second thing is, for reasons which will become clear, is known as Shannon's entropy. This is the Shannon's way of dealing with it, and the more common application today in physics is due to Shannon's entropy. So we have already identified that information or a measure of information is connected with an uncertainty. So therefore, let us define a random variable. Supposing I define a random variable x, let me recall for you some standard notations of statistics where the event itself, the random variable itself, is given by a capital letter, and the values that variable can take is given by small letters. So we talk about a random variable x corresponding to physical processes which have possible outcomes, which I will write as x1 which occurs with the probability p1, x2 which occurs with the probability p2, etc., etc. And let's suppose there are m number of events, xm occurs with the probability pm. Since the total probability is 1, so I have sum over I, pi, I equal to 1 to m is equal to 1. Now let us define a function which I will represent by h, and say it's a function of the probabilities p1, p2 of various events, pm, and this is the average uncertainty associated with an event x equal to xi. Now you can also interpret it by saying that this is the quantity which represents the amount of uncertainty that is removed when we know the result of an experiment, that it is equal to x equal to xi. And this obviously is a function of all of these. Now my job will be to have a mathematical expression for this quantity. In order to do that, let me define certain auxiliary quantity. Consider a situation where all my p's are the same. In other words, if I have m events, each one of the p's is 1 over m, 1 over m, 1 over m, etc. And let me define that by a function f of m is equal to h of, so it's actually a definition 1 over m, 1 over m, etc. m terms. What does it actually mean? It means that suppose you are doing a coin toss. Now I know that in a fair coin toss, I have only two events, P1 is equal to half, P2 is equal to half. So my f of 2 is h of half half. So that's what is meant by this function. Now the other thing which becomes obvious for the property of this function f is that f of m must be a monotonically increasing function with increasing value of m. Now look at what it means. See, supposing I am talking now about if I am saying if m is greater than m prime, then f of m must be greater than f of m prime. Now that is very obvious because take the example of a coin toss. Now I have only two alternatives. So if I have two alternatives, my corresponding f of m is 1 by 2, 1 by 2. And supposing I am talking about throwing of a die, then obviously I am talking about 1 by 6, 1 by 6, 1 by 6. In other words, f of m is a monotonically increasing function. F of m is a monotonically increasing function of m. Some other interesting properties follow. For instance, suppose I consider two random variables. One I call as x, another I call as y. Just to be specific, let us suppose x is the coin toss which has two alternatives and y is throwing of a die which has 6 alternatives. And supposing I want to do a joint experiment. What does a joint experiment mean? It means I throw a coin and I throw a die and I get various alternatives. So for example, I could get a head with any of the 1, 2, 3, 4, 5, 6 or a tail with any of the 1, 2, 3, 4, 5, 6. So my number of alternatives have gone up. The possibilities then that is there is that this must have this property and f of m times n must be equal to f of m plus f of n. Now this is actually obvious because when you do a joint experiment, the number of alternatives go up. M times n becomes the number of events. But if you know the result of, let us say, the first group which had m events, that doesn't help you remove the uncertainty associated with the second event, which is given by f of n. So if I know the result of a coin toss, I still have an uncertainty function defined by f of 6. On the other hand, if I know the result of throwing of a die, whether it is 1, 2, 3, 4 or 5 or 6, the uncertainty with respect to what happened for the coin toss, whether it was a head or tail, still remains. So therefore, I must have f of mn equal to fm plus fn. Another obvious property is f of 1 must be equal to 0. If there is just one event, there is no uncertainty associated with it. It's called a certainty. So since there is no uncertainty, f of 1 must be equal to 0. There is another property which is important. It takes a bit of a time to work out. Since I am not going to be giving a course on classical information theory, I will not work it out but show it to you with some examples of how it works. And this is what is known as a grouping theorem. The proof is found in any classical information theory book, but basically a grouping theorem talks about, suppose I have a random variable x with m different possibilities and whatever we associated probabilities called p1, p2 up to pn. But let us suppose I divide them into two groups. Let us call it group A and group A, which has R events, and these R events are x1, x2 up to xr, with probabilities of course p1, p2 up to pr. And group B is, well, essentially the remaining events, which is x r plus 1, x r plus 2 up to xn, and with corresponding probabilities pr plus 1 etc. up to pr. Now what the grouping theorem does is to say that this uncertainty, which we have said is given by p1, p2 up to pn, which is equal to h as a function of the first group probability, which means it is I equal to 1 to r of pi, and second group probability I equal to r plus 1 to m pi, and that happens to be equal to sum over I pi, then the h associated with these events. Now notice what is this. So I have p1 by, now the normalization, because I know its event in group A, is sum over I equal to 1 to r pi etc. And a similar term, sum over I equal to r plus 1 to m pi, and similar thing, but now it will be in the slide because I don't have writing space here, but now the denominator is from I equal to r plus 1 to m. Look at the slide for the exact structure of the equation. This equation is derived by using what is known as Bayes' theorem in statistics, and as I said, takes a bit of a time, so I will probably put it on the lecture note associated with this set of lectures, but proof I will not do it here. But just to illustrate what the grouping theorem meant. So suppose I consider two groups. Now I have a group A in which I have two events. Probability of the first event is half and the second event is 1 by 4, let us say. So the total group A's probability, so let me write it as a PA, is equal to 3 by 4. There is a group B in which I again have two events with, let us say, equal probability. So P3 equal to P4 equal to 1 over 8 each, so that P of B is 1 by 4. So if I look at the total uncertainty for the whole event, what the grouping theorem tells me is H. So let me first write down all of them. So I've got half, 1/4, 1/8, 1/8 minus H of 3 by 4, 1 by 4. Now that would be equal to, choose the event A, which is 3 by 4, and now I need the probability within a group. So you notice that within this group, given that the group is A, this probability of P1, probability corresponding to P1 would be 2/3, and this should be 1/3 because you can see this is half that of this one. So total probability within a group being equal to 1, the first one has probability 2/3, the second one has a probability 1/3, and likewise for the second group whose probability is 1/4 times the probability within a group of the two events there, but since these are equal, so each must have the probability half and half. Now what I am going to do in the next lecture is to look at these properties and find out, is there a function that I know which satisfy these things? What are these things? F of 1 is equal to 0. It's a monotonically increasing function of its argument. F of m times n is equal to f of m plus f of n. And finally, a statement of grouping theorem remains valid. We will see next that this is given by a very well known function, and I will identify that with what I will designate as entropy or Shannon.